All right. Thank you so much for that introduction. I think that covers indeed everything. And yeah, I'm happy to talk a little bit about what I've been doing in the last 4.5 years in my PhD at KDH on leveraging non-expert feedback or human feedback to correct robot behaviors. Robots have typically shown success in structured environments and confined spaces. For example, here you see an ice cream robot that's delivering ice cream to people here in Stockholm this summer. But even in confined spaces, robots still might fail. I think this is in Poland. It's a hot dog making robot, and it's trying to make a hot dog in a bun. And I'm saying trying to because you can see that it fails to put the sausage in the bun. And all you end up with is your sausage. So if we want to deploy robots in unstructured environments or even with humans in the environment, there are more uncertainties that arise and more possibilities for the robot to fail. For example, let's imagine a cooking robot in a kitchen that is tasked to serve us dinner and put it on the table. If the robot is trained or has learned to fetch a tomato slice, it will fail if there's no more tomato slices available and only a whole tomato. It has to learn that it first needs to cut the whole tomato into slices. Or if it's placing a coffee on the table, the user might prefer the coffee to be closer to the plate. And it does not like where the robot puts the coffee on the table if it's very far in to the edge of the table, for example. And when the robot is moving around in the kitchen, the trajectories of the robot or the robot's behavior might be perceived as unsafe, and people might feel uncomfortable with the robot's behavior. And so in my thesis work, I defined robot failures as when a robot fails to successfully execute a task or to do so in a way that aligns with people's preferences. And typically, when a robot fails, experts are called in to resolve the robot's failure. But there's not always an expert available, or it can be costly to call one in every time the robot fails. And in many daily tasks, for example, the cooking scenario that I just showed you, people who are not necessarily programmers or roboticists might be able to provide additional rules. For example, if the robot sees a full tomato, we can tell it to cut the tomato into slices first if it wants to obtain a slice. But if we consider human input to correct robot behavior, we need to make sure that what we tell the robot to do is also what it actually will do. So we need to verify the robot's behavior. And so in my PhD, I have tried to explore this approach where we have human input as a formal specification or as structured as a formal specification, because then we can synthesize robot behavior or correction mechanisms over the robot's behavior. And in the end, we end up with correct verifiable robot behavior. So this is the overall approach that I've been exploring in my thesis work. And the overall goal of this research is to leverage non-expert input to develop robust and verifiable robots that can successfully operate around people. And so in my thesis, I have looked at two different kinds of non-expert input: what the robots should do, so task goals and task constraints, and how the robots should do it. For example, preferences of where to place a coffee mug. And today I want to highlight two of the works that I have done in my PhD. And the first one is considering what the robot should do. So specifying task goals and task constraints. We can imagine that, I don't know how many of you are left-handed, but I am. And every time I order a drink, people place it on the right side of my plate with the handle. If it's a mug, the handle is on the right side. And I always need to turn it around and put it on the other side of the plate in order for me to be able to drink from the cup. And so I would like to specify to my robot, if it gives me my coffee, that it needs to be left of the plate and potentially even with the handle on the left. And so these kind of spatial relations between objects, people might have preferences over and might be able to specify these relations when we are training our robot. So in this work, we were motivated by the question of how can we leverage human input in dataset generation for data-driven robotic tasks. Specifically, we use a framework that's introduced by my colleagues at KDH called Spatial. And with this framework, we can specify task goals and task constraints. So for example, that I want the mug to be left of the plate. And we can measure the extent with which we are satisfying or violating the specification. And we can do so in continuous space. So for example, if I have a mug and a plate in the scenario, I can give you how much we're satisfying the specification of mug left of plate, and we can move the object around, and at any time we can get this satisfaction value, whether we're satisfying or violating the specification. And examples, for example, of spatial relations are left of, close to, above of, that are defined in the spatial framework. And the spatial relations themselves are not necessarily easy to define by non-experts yet, because we need a notion of what it means to be left of and compute this score. But if we create these spatial relations, which can be added to the framework, we can use these higher level spatial relations, left of, close to, and above of, can be used by non-experts. And so the approach that we propose in this work is to generate new training scenarios or even testing scenarios for robotic manipulation, given a desired goal configuration. So for example, me wanting my mug left of the plate, I can give that as a specification, and then we can create training data, which I will explain in a minute of how we do that. And we can train generative models with this training data and a desired specification satisfaction value for the specification. And then we can generate new scenarios given a desired specification. So I can create new scenarios saying, I want examples where the mug is left of the plate. Or the other way around, I can say, I want examples where the mug is not left of the plate. So we're violating our specification. So we first generate training data. We create random object poses, for example, for a mug and a plate in a scene. We have X and Y coordinates for each object and the orientation, because, for example, with the mug, I wanted to handle on the left, or if you have a knife on the table, you might want the sharp end to be pointing away from you. And then for each scenario, we can compute a satisfaction value. So on the right, you see examples. This first example is where the mug is not left of the plate. The mug is the blue dot and the plate is the orange dot. So here we have a negative satisfaction value because the mug is right of the plate. Here, the objects are closer together, but the mug is still right of the plate. In this case, the left-of spatial relation is defined as the distance between the objects and whether the x-coordinate of the mug is, in this case, lower than the x-coordinate of the plate. So in this case, they're closer together, but still the mug is right of the plate, so we have a smaller negative value. The third example here is a satisfying example. Now the mug is left of the plate in this case. And the last example there, also the mug is left of the plate, but with a larger distance, so we have a higher satisfaction value. And so we can have different examples with different satisfaction values. What we could do is create a lot of training data and then sample out all the samples with a certain satisfaction value. Let's say I want a satisfaction value of 0.89, which I have here. I can just create a lot of training data and create some sort of lookup table and get all the examples that have that value. However, we need a lot of training data, and so instead we want to see if we can condition a generative model on the satisfaction value so that we can generate new scenarios that correspond to a certain satisfaction value instead. So we, in this case, in this work, compare two commonly used models, a generative adversarial network, or GAN, and an adversarial autoencoder, an AAE. In this case, I will skip the details on the model due to time, but I'm happy to answer questions about it, or it's also in the paper. But we compare these two models to see if they can be used, if we can condition them on the satisfaction value, and if we can use them to generate new scenarios that adhere to these spatial relations that we define. And so in the results, we can see, for example, here where we specify that the mug needs to be left of and above of the plate. The mug is in this case the dark dot, and the plate is the white circle. We can see from left to right violating to satisfying examples. So on the left, you can see that the mug is not above of the plate, it's below of. And as soon as one part of the specification is violating, we have a negative satisfaction value. This is how it's defined currently in the spatial framework. And you can see on the right that in that case, the mug is left of and above of the plate, so we have a satisfying example. And we can also create or define task constraints. So for example, that the mug needs to not be so close to the plate. So for example, we want to say objects shouldn't be too close to each other. This might be for safety, but also that the robot might still be able to get its gripper between objects. And so in this case, we say the mug should not be close to the plate. And you can see again on the left, violating examples where the two objects are very close together. And on the right, you can see satisfying examples where the objects are far away from each other. So in this case, not close to means far away. So in that case, we're satisfying this specification a lot. If we look at different examples, so here we have a video that's going to play. Or you see on the bar below satisfaction values, we start with negative ones where we're violating the specification. The specification again is mug left of plate and mug above of plate. So the violating examples, the mug will either be right of or below of or both of the plate. And you can see here the different generated scenarios if we give a satisfaction value to the generative model and we create a new scenario with that. And the closer we get to 0, the closer you see that the objects are getting to each other, and then it flips. So now when we have positive values, the mug will be left of and above of the plate. And the more we're satisfying our specification here, the more it's driven towards the corners of the table because of how the spatial relations currently are defined in spatial, where we measure the satisfaction based on the distance between the objects. So we can also include more objects and more complicated specifications. For example, this specifies to set a table setting scenario. So you can see the visualization of the specification below. The plate needs to be on a placemat, the knife needs to be right of the placemat, and so forth. And if we have more objects and more spatial relations, we evaluated the performance of the two generative models to see what is the difference between the scenarios that they generate. And so when we compare on the left, you see our randomly created training data. And here we filtered out the positive examples only, so the ones that are satisfying our specification. And you can see in the middle that the GAN generative network is very accurate. So it creates new scenarios, but it places the objects relatively close to the original position of the objects. So they're not very much spread out on the table, but if you compute the satisfaction value for these newly generated scenarios, the score will be very accurate to what you actually requested from the network. On the right, you can see the results of the AAE, and you can see that they generate more diverse scenarios. So in this case, the objects are placed over a larger area of the table. So for example, the red cracker box, it's spreading out, or it's covering more of the left top part of the table. So we get more diverse scenarios in that sense. However, if we then compute the satisfaction value for that scenario, it might differ a bit from the desired value since it's based on distances, and if it's then placed slightly elsewhere, the score might also change a little bit. However, the overall conclusion of our work is that we can condition generative models on user specifications, such as my coffee needs to be left of the plate or right of the plate, to encode these desired spatial relations in scenarios for data-driven robotics. And so this work was focusing on what the robot should do, so where to place objects and putting constraints on the relations between the objects. And now I want to talk a little bit about how the robot should do what it should do. So we can have preferences over the robot's behavior, and how can we include that into robot behavior? So specifically, I want to talk about including input for autonomous vehicles. So in human-robot interaction, we are interacting with the robot, and if it behaves in a way that we do not prefer or we do not like, we might not accept the robot and we might not want to use the robot. And this holds also for autonomous vehicles. Driving styles play a major role in the acceptance and the use of autonomous vehicles. We all have our own way of driving. Some of us might prefer more aggressive driving style. Some of us might prefer more defensive driving style. And if you sit in a car that's objectively safe, but it still might drive in a way that you do not feel comfortable with, it's very likely that you're not going to use the autonomous vehicle again. And so different driving styles can be learned from human data. So we can try and learn our own human driving styles, um, for example, through inverse reinforcement learning. But these neural network-based techniques are usually still black box models. And it's very difficult to give any certification on the behavior of the vehicle. And this is very important if we're dealing with real-world traffic scenarios and road rules. So my colleagues at KDH have tried to, or have worked on encoding road rules in motion planning through signal temporal logic. And this is similar to the work that I just described with the spatial framework that can measure the extent with which we're satisfying or violating a specification. In this case, we are encoding speed limits, safety distances. For example, we say that the car needs to maintain center line, so it should stay in the middle of the lane. All these characteristics can be defined through signal temporal logic. And the quality of signal temporal logic is that we can again specify or compute how much we're satisfying or violating our set specification over a whole trajectory and all road rules. Because, for example, if we have a car and we tell the car that it needs to stay in the middle of the lane, in that case, we will not be able to take over a car that's in front of us that's going much slower, and so we might get stuck behind it. So in some ways, or at some points in time, we might need to violate our specification for just a little bit, just to be able to, for example, take over a car and then go back to the middle of the lane that we were in. And so if we want to sometimes violate our specification to be able to effectively get to our goal, we also need to compute how much cost we assign to violating our specification, just to make sure that the car is not just violating our specification all the time, because we still want the autonomous vehicle to drive according to our specification. And so my colleagues defined a penalty function W, and it basically denotes how much cost we give to violating our specification. And this cost function has two parameters. Parameter alpha, which denotes the maximum violation that we allow. So if the autonomous vehicle is violating more than alpha, we give it infinite cost because we do not want that to happen. And if we're satisfying the specification, we have a cost of 0. And A, the parameter A here denotes the cost step between this, where we're satisfying, and until we get to alpha, so our maximum allowed violation of the specification. A denotes with how much the cost increases between satisfying and getting to our maximum violation. And so in this work, we are motivated by the question, can we calibrate these two parameters to generate trajectories that correlate with distinct human driving styles? So we created a study that was set up as follows. We had 4 different urban traffic scenarios, a roundabout, an intersection, a chicane, and a takeover. And we implemented and recorded traffic scenarios, these 4 traffic scenarios, in a car life simulator with different driving parameters, so alpha and A. And we computed a defensiveness score over each trajectory that we generated. And this defensiveness score was taken from prior work, and it includes features like the speed that the car takes in a turn and the distance that it keeps to other vehicles in the scene, for example. And then we asked participants in an online study to evaluate the trajectories and rate them on how defensive or aggressive they think the trajectory is. And then we wanted to associate driving styles to different sets of parameters. to see if we can encode human driving styles in motion planning for autonomous vehicles. And so in an online study with 35 participants, people saw trajectories, and they rated the trajectory based on defensiveness. So they rated it on a scale from very extremely defensive to extremely aggressive. And we also asked them which trajectory they preferred from a pair of trajectories, in order to see if they preferred a driving style for an autonomous vehicle that matches their self-reported driving style. And so I want to show you an example. Here's the roundabout scenario. On the left, you can see defensive driving behavior. In the middle, the neutral condition, and on the right, an aggressive driving style. And you can see that the aggressive car enters the roundabout even before the other car, while the other two are waiting, and the neutral one goes on the roundabout slightly earlier than the defensive one, which keeps an even larger distance to the other vehicle. And similarly, in the intersection scenario, again, defensive on the left and aggressive on the right, you will see that the aggressive car, it stops slightly, but then continues quite soon after it stopped. And it's very close to the other car, whereas the other ones wait longer, and the defensive one takes the longest to complete the intersection. And so we showed people these scenarios, and then we looked at how aggressive they rated our trajectories. And on the left, you can see on the y-axis the defensiveness score. So that's important to note that it's defensiveness score. So in this case, we can see that the aggressive driving style was rated the least defensive, which makes sense. So it was the most aggressive. Whereas the defensive driving style was rated the most defensive. So we found that these parameter calibrations actually correlated or corresponded to the distinct driving styles that we were trying to model. And then if we looked at which driving styles people preferred, on the right, you can see that most people prefer the defensive driving style, which is in this case the blue in the graph. And we had people, some people started with seeing first a very defensive driving style and then a very aggressive, and vice versa, to see that the order didn't matter. And in this case, you can see that if you started with a high defensiveness score or with a low defensiveness score, in both cases, most percentage preferred the defensive driving style. And so the overall conclusion of this work is that we can encode road rules and distinct driving styles in motion planning for autonomous vehicles. So this was more on how we can incorporate or encode human input into how the robots should behave. And my work has looked at these two types of input, what the robots should do and how the robots should do it. And in the end, the goal is to have an automated correction pipeline to correct robot behavior whenever it fails to complete a task or when it fails to do so in a way that aligns with what people prefer the robot to do. And so in the future, there's still a lot of challenges left to research. And one of them is to deal with ambiguous and incorrect feedback. We're asking people's feedback, but people might not know the correct solution in some cases. And we need a way to distinguish if feedback is actually correct and if it's ambiguous, what it means before we're deploying that feedback on the robot. We need to make sure that it is actually what we're looking for. And it's also, since I'm looking into non-expert input, and a lot of people that are not roboticists or not programmers do not on the daily think about forces and torques and low-level robot control. And so we need to find the right level of abstraction for people to give input to the robot that's still expressive, but also understandable for people who are not necessarily experts or roboticists. And what this level of abstraction is needs to be researched more. And furthermore, a lot of the work that has been done, and also my thesis, is part of it. So it's part of this full pipeline, but we need to connect the dots. And we have a full closed loop correction pipeline with automated formal synthesis with a real robot. And then when we have a real robot, we also need to think about how to abstract its environment and the information about the failure that we need to send to people in order for them to understand what happened and how they can help the robot to correct its behavior. And all this work in the end then would lead to a way to leverage non-expert input to develop robust and verifiable robots that can successfully operate around people.